of this open set V do not intersect. Therefore, we can take a point X in V and a ball around this point, and then compare these balls and get one side. We have done this before the break. Now, suppose, let us prove the converse. Suppose such X and epsilon exist. Then, if we take Fs of X and if you take Fs of X and Ft of X, then we'll have that this distance is with Fs minus 1 Ft of X, and X will be greater than epsilon. Therefore, we can choose, for example, epsilon divided by 3 balls, which will not intersect in these copies. And if we consider the union of images of such balls, then we'll get an open set. You see, suppose you have such a ball that for any Fs and Ft which are incomparable, Fs of B intersection Ft of B is empty. Then we can take the open set as the union of all Fs of B. And this union will satisfy the conditions of this where S, so of all Fs in G of S. Why? This union is an open set, first. Second, if we applied some Fs to this union, we'll get a subset of V. Yes? And if S and T are incomparable, the images will not intersect. So this is the first statement. The second is very interesting. So if OSC holds, then we have this. But we need to prove that OSC is equivalent to this condition, that identity doesn't lie in the closure of the associated family. For this condition, we'll have the following way. So suppose if identity doesn't lie in the closure of F, if identity doesn't lie in the closure of F, then there is such epsilon more than 0 that Fs minus 1 Ft, the distance between Fs minus 1 Ft and identity is more than some epsilon more than 0, right? If these pairs are the family of all these neighborhood maps is separated from identity, then there is some distance between identity and other map and other maps which is greater than some epsilon. But what is the This means that what does it mean that some map differs from identity on some epsilon? How we define the distance between maps? We fix some basis, and if for if there is some base vector for which fs minus 1 ft of ek minus ek is more than epsilon, this just means that the distance between this and this is more than epsilon. Right? Because if for all the base points the distance is less than epsilon, then the whole distance is also less than epsilon. Okay. So this is also obvious. But there is slight difference. Slight difference. Here we have 1 point, and here we have 1 point chosen from some finite number of points. There is one more statement which we need for band graphs theorem. This is the following. So do you remember the natural measure on K, which we introduced yesterday when we considered the open set condition? So we have, suppose we have a self-similar set, K equals F1 of K union Fm of K, right? And let alpha is a similarity dimension, Q1 to the power of alpha plus Qm to the power of alpha equals 1, right? And suppose that Hausdorff dimension of A equals to alpha. Then what will happen? Then we consider the natural measure on the set A, which is the projection of invariant measure, S-dimensional invariant measure on I infinity. So we have a projection pi from I infinity to the attractor. Suppose and mu wave is the mu wave of some set B equals the invariant measure mu of pi minus 1 of B. So I have a self-similar set, and suppose the copies of this self-similar set have the intersection of these copies has non-zero measure. So if measure of AI intersection AJ, it means the copy AI and copy AJ is not zero, then the measure of preimage of Fi intersection preimage of the preimage of Fi intersection is J is positive. Yes. So we have the set I infinity, and the I infinity is a disjoint union of the set I infinity 1, I infinity 2. So these are the copy. So 1 I infinity, 2 I sigma 1 of I infinity, sigma 2 of I infinity, etc. Yes. And for some two indices, the preimage of this intersection lies in both copies and have positive measure. Then we can take some cylinder in one of these preimages, and if we delete it, then we'll get that. Oh, 1 second, sorry. Sorry, 1 second. So we'll find two cylinders here, such that their images do intersect in K. Therefore, we can erase this one of these cylinders and find that similarity dimension is different from initial, and it is greater. So this is the way how it proved. How it is proved. So and now we can proceed to the proof of the theorem of band and graph using these properties. So suppose that identity is not contained in the closure of F, in the closure of the associated family. Then we take some base points x0, x1, xd in X in the space Rd. So we take these points, sorry, X in this set in the attractor, and these points are in general position. So for any and suppose there is epsilon, such that F intersection epsilon neighborhood of identity is empty. So since identity is not contained in the closure of F, then there is a neighborhood of identity which doesn't intersect this family of all neighborhood maps Fi j minus 1 Fi. So if we have, let it be T and S, Ft minus 1 Fs. So for any T and S, there is such J, such that F T minus 1 Fs of Xj minus Xj is more than epsilon. So we have identity, yes, and we have pairs, the neighborhood maps Ft minus 1 Fs, and it differs of identity, but it differs on one of these base points, of one of its base points. So we'll have very interesting picture. So if we consider all these maps, so we have Ft, Fs, small f. Here we have small f. If for any incomparable multi-indices, we have some g, such that Ft of x, Ft of x, Ft of xj minus Fs of xj. So you see Ft minus 1 Fs of xj minus xj is greater than epsilon, then Ft Fs of xj minus Ft of xj will be greater than the coefficient of t multiplied by epsilon. We have such a difference. And then we'll get we consider some set. Consider some small ball U and consider all the copies. One second. Consider a small set U and consider all the copies which intersect U and have approximately the same size as U. So we can think that diameter of A is equal to A. So we'll define the family of all the sets which intersect the ball U. If we take the ball U and consider these sets which intersect it and have approximately the same size, and at the same time they have incomparable multi-indices, then following the pattern which we used for open set condition, we can evaluate the size of U. But the problem is that these sets may intersect each other, because open sets do not. But in our case, we have no open set condition. We have no open set condition. We have only this inequality. So we need to find such a way how to evaluate the number of sets of sets with incomparable multi-indices which intersect U. There is one very interesting property, that if we have the set K, and if we have chosen the points x1, x0, x1, x2, xd, yes, then for two incomparable copies among these points, there will be some j for which the balls around these points xj do not intersect. So in the case of open set condition, we had just non-intersecting balls lying in the open set, and these balls allowed now us to evaluate the number of all possible incomparable copies. We took this open set, we took some ball, then we took a larger ball, and we considered this non-intersecting open set, put smaller balls in this open set, and found the maximum possible number of these balls. But now we have more strange situation. We have more strange situation because we have with each ft of k, we associate a family of d balls, of diameter epsilon multiplied by qk. Yes? And for any two copies, it may happen that one of the balls differ and the other coincide. So we have, if we consider the family of all copies which intersect given open set U, then we'll have the following. Since the multi-indices for these copies are incomparable, we can draw a graph. So this graph will denote these copies, and for any two copies, there is an edge which is marked by one of the numbers 0, 1, 0, 1, d minus 1. So, because we have d balls, yes, some may coincide, but there is only one for which its images do not intersect. Therefore, we have a graph whose vertices are connected by edges, and each edge is marked by one of colors, 1, 2, 0, 1, D1. Yes? So we'll get a graph which is color whose edges are colored in D colors. So if in this graph we choose a number of vertices which are connected with the same color, then these balls do not intersect and their maximal number is bounded. Maximal number is bounded because we take a large ball and divide it by the size of this ball and such number of. So to prove this fact, we need to remember the Ramsey's theorem. Do you know Ramsey's theorem on graphs? Ramsey's. There is a problem which shows what does this Ramsey's theorem means. Suppose there are 6 persons. Please prove that either 3 of them know each other or 3 of them do not know each other. Do you know this problem? We have 6 persons. 6 men, 6 young men. Some of them are friends, some of them are enemies. So let us consider, is it possible so that among these 6 persons are 3 friends or 3 enemies? Okay, so we can draw the edges connecting these points. So if I choose some person, then he has relation to 5 other ones. And from these 5 other ones, it may happen that they are all friends. It may happen that there are 4 friends and 1 enemy, or 3 friends and 2 enemies. So in any case, this person has either he has 3 friends or he has 3 enemies. Suppose this person has 3 friends. So there are two cases. If these guys are enemies between themselves, then we have a triangle. Yes, we have 3 enemies. If these guys are not enemies between themselves, then 2 of them are friends and we have a triangle again. Yes? So it means that any graph with 6 vertices colored in 2 colors, whose edges are colored in 2 colors, contains a triangle of 1 color. So this is a very short formulation of Ramsey's theorem. For for any m and any k there is such m large of m and k that each graph with more than m vertices, more or less than m vertices, colored in edge colored in k colors, contains a complete subgraph of one color. You see? Any two-colored graph with 6 vertices contains a complete one-colored triangle, right? No matter which color we choose. And this number is called Ramsey's number, and some of these numbers are computed. But majority of these numbers is unknown. We just know their existence. What will be the usage of this Ramsey theorem in our situation? In our situation, we consider a graph whose vertices are colored in D colors. Yes? And if it contains a complete subgraph consisting of which has m small vertices, yes, then the number of vertices is in this graph will be less or equal than m large elements, yes? Large elements. Therefore, we consider the following way. We take the set U, we take a large ball around it, divide it by the size of a ball of diameter epsilon, count the number of these balls, it will be m small. Having m small and this number d, we have m large, yes? And m large will be the maximal possible number of copies intersecting U. Yes. And if we have evaluated the maximum possible number of copies intersecting U, then we have an evaluation of the measure of this set U, right? Just the same way as we did, and we get have the inequality that measure of U will be less than C multiplied by radius of this ball to the power of S. and then we apply the mass distribution principle and see that the dimension is greater or equal than S. So this is the idea of Van Graaf's theorem, of the proof of Van Graaf's theorem, and it is based on Ramsey's theorem, but the most important condition which we have is this, that if identity is not contained in the closure of the associated family of similarities, then if the identity is not contained in the closure of the associated family of similarities, then sorry, then yes, the dimension, Hausdorff dimension of A is more than F, is more or equal than S, and the measure S-dimensional measure of A is positive. Okay. So this is Van Graaf theorem, and later it was developed by Andreas Schiff. And now I will proceed to some other matters, because maybe I will have some more time to explain this today. So what we have, yes, now we have this lecture, and after that we have a tutorial at 1:30. Maybe I will continue this topic at 1:30. And now let us consider the problems of how to construct a three-dimensional object in IFS style. I don't understand. Does it sleep? How to? Oh, okay. Thanks a lot. This power is on, and now, okay, technique now. Source. sources, HDMI front. One more. Okay, that's all. Enter, 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 enter. Yes. Enter. Okay. File, open. Escape. I wish to open some three-dimensional file. Oh, sorry. Okay. Coherent. What is it? Okay. Present. No. Sorry. 1 second. I will apply. Examples. 3D simple. Okay. So let us look how the Sierpinski tetrahedron is constructed. So what is the difference between one-dimensional or two-dimensional and three-dimensional case? So if you look here, you will see that the program for building this tetrahedron is very simple. Do you see it? Yes. So we give the dimension 3, define dimension 3, define the name just in case, so that we don't mix it with some other objects. And then we take 4 vertices of a cube. We take a cube and its 4 vertices. One, say 2, then 3, and 4. Oh, here are odd vertices. So if we take odd vertices, it will be 1, 0, 0, 0, 1, 0. Then it will be 0, 0, 1, 0, 0, 1, 0, 0, 1, and finally we'll have 1, 1, 1. This is not here. 1, 2, 3, and fourth this one. That is enough to construct this object. But even if we slightly change some of these vertices, nothing crucial would happen. For example, if I make this, replace this by 2 and apply it, then I'll get a Sierpinski tetrahedron again. and I can rotate. Oh, 1 second. I didn't install the last version of this program in which the rotate, three-dimensional rotate bug is overcome. Okay, so now you see this. So if I change this for 2, nothing really happens because this definition is good for all kinds of coordinates. It just changes the size, but oh, now it rotates. Okay. So you see how it works. In this case, in three-dimensional case, the vectors have length 3 and matrices have length 9. Matrices have length 9. It is much more. So I will show you one more example. One second. Oh, this one. Okay. We already discussed it, and it is the Antoine's necklace, which is very simple, but of course it needs some procedures. Oh, sorry, 1 second, I need to look at it. So I will consider it. Editor. So we need rotation in Z, rotation in Y, and rotation in X. Oh, these rotations are defined the following way. Rotation in Z is rotation in Z will have a rotation in Z of alpha will be a matrix of the following way, type. I mean, it will be cosine alpha minus sine alpha 0. Then it will be sine alpha cosine alpha 0 and 0, 0, 1. Do you see it in program code? And I don't see it. I just try to remember. I don't understand why I don't see it. Where did you find it?
Basically, we are putting the Z constant and rotating, so we just...
Yes, I understand that. So you didn't see it in the program. What? You just imagined it. So we have these three operators: rotation in Z, rotation in X, and rotation in Y. And this is enough. So we have one map is contraction and translation to the axis y, and second map is quite more complicated. Second map is quite more complicated. We have rotation in z, then we have a translation to 1 in the axis y, then we have a... So what we do? So suppose we have this figure, yes. So first we take the smaller image of this figure translated to some vector, and second we need to make a perpendicular image which is translated this way, and then we begin to just make, you make S1, we make a group S1, S2, and after that we begin to rotate them by pi divided by 6. 1, 2, 0, 1, 2, 3, 4, 5, 6 times, and then 12 times. And this is the way how this Antoine's necklace is obtained. Do you need it? If needed, I can send you the code, and you can implement it on your laptops. Okay, so do you have any question connected with your assignments? What? I don't hear. Need I come to you? You have the question?
This one actually, we have to find the coordinates of this and then translate.
Rotate.
Okay. How to
Yes.
find the coordinates?
The coordinates. This problem is that these two pentagons need to intersect in one point. So let us check. Suppose we have a large pentagon, and then we take a smaller pentagon, smaller ones. So we have this is Q, right? So if this is side is 1, then it will be Q, and Q will be the same, and then you take Q. You know this angle, yes? You know the angle, yes? Because if you have a pentagon, what will be this angle? It is 2 pi divided by 5, yes. So I will write it alpha, 2 pi divided by 5, yes. So we have Q, 1, 2 times, and Q cosine alpha 2 times. So q multiplied by 2q multiplied by 1 plus cosine alpha is 1. Alpha is known. This way you find the q, right? What? That is enough. We just need to find one parameter. Okay.
And how does we have to rotate it?
Get rotated. Oh, I explained yesterday. Because rotation of a regular polygon, if you have a regular, some regular polygon, maybe this way, yes. So we have this angle 2 pi divided by n, right? If we rotate this polygon by the angle 2 pi divided by n, we'll have a parallel copy of it, which is shifted by a side of this polygon, yes, backwards. So you need to rotate and then shift one to the right. Then you'll get a polygon whose sides are equal to 1 and which has n sides. More questions? Your questions? No? Okay, it works. Can I look here? No, it doesn't work. So my laptop is discharged and I cannot switch this one. Oh, oh, thank you. You're a magician. Yes, I know that this is a time, but I try to observe the exact time. Yes. So yeah, you can consider this moment as the beginning of the break. And today is Saturday, right? Saturday. It's 12:00, so we have lunch time, and then we have a tutorial at 1:30.